As much as I like the fact that nonparametric methods can provide exact probabilities, sometimes the computational requirements are just too large to be able to calculate these probabilities. In those cases, we can turn to large sample approximations. The very first inferential method that I introduced in my first video series in nonparametric statistics was a hypothesis test for a population proportion using the binomial distribution. I would be surprised if in your very first statistics course you did not see a formula like this. When we first learn how to test a population proportion, it is done in the context of parametric statistics, so we calculate a z-score, that is a score from the normal distribution, using our proportional estimate of the parameter that we hypothesize. We take the difference between the statistic and the hypothesized parameter, divide by the standard deviation of the statistic, and then assume that this is on a normal distribution so we can calculate a z-score. Why are we able to do this? You might also remember when you learned this formula that you also saw something like this, the sample size requirements before you can use the formula. You might have seen a different variation of these requirements. Some people use 5 in place of where I have 10. Some people use 15 in place of where I have 10. But the point here is that we have to have a large enough sample in order to be able to do this hypothesis test. That is because with a large enough sample, we can approximate the sampling distribution of a proportion with the normal distribution as a result of the central limit theorem. Now, having watched the video in which I used the binomial distribution in order to conduct the hypothesis test, you should know that due to the binomial formula, we never need to use this approximation, no matter how large the sample. The only reason that this is our first introduction to a test of a proportion is because we are taught this in the context of normal distribution theory, which is usually how all inference is presented in a first statistics course. From now on, however, you should use the binomial formula. You can use it for any sample size, and it will give you exact probabilities instead of the approximate probability that you would get with this formula. I am referencing back to your first statistics course to show you that you actually learned large sample approximations already. You just didn't know it at the time. Now, if you were to use this formula, you would be doing it as a large sample approximation. But as I've noted here, there is no reason to use a large sample approximation. The computing requirements will never get too big so that we have to use this. However, with many of the nonparametric methods that we have learned and will learn in the future, the computing requirements will get enormous. Does that mean that we have to start using parametric methods? Not at all. We can still use nonparametric statistics, but now we're going to have to use approximations of the probabilities rather than exact values. The reason that we can do this is the same reason that we learned when we first learned parametric statistics, and that is the powerful central limit theorem. The central limit theorem states that the sum of independent and identically distributed random variables will approach the normal distribution as the number of variables increases. And indeed, the statistics that we are calculating, even in nonparametric statistics, are sums of independent and identically distributed random variables. The large sample approximation that can be used for a test of proportion works because a proportion is a sum of independent and identically distributed random variables where each of those random variables assume values of 0 and 1. It is important to note that the rate of the approach to the normal distribution, that is, how good the approximation is, depends on two things: the underlying population distribution and the statistic we are using. When we draw from different types of population distributions, the approximation is going to work in different ways. For some types of population distributions, we'll need bigger sample sizes than others in order to obtain a good approximation. Similarly, with different procedures, we're going to use different statistics, and that can also influence how big of a sample size we need in order to obtain a good approximation. The accuracy of normal-based approximations depends not only on these factors, but also the sample size. It is important to keep this in mind so that you know that the fact that you are going to use a large sample approximation doesn't mean you should stop thinking about the underlying population distribution or which nonparametric methods you want to use. Those two factors and the number of observations you have are going to determine how good the approximation is. Here are some basic ideas to keep in mind when you are considering large sample approximations with nonparametric methods. First, the only reason that we're turning to such methods is that we don't have enough computational power for an exact method. That means that our sample size has grown so large that we can no longer calculate exact probabilities. How large is that? It depends on the nonparametric method you are using, as well as the algorithms available to you to calculate exact probabilities for those methods. So there is no one sample size rule here. It depends. All of the large sample approximations rely on the central limit theorem and thus use the normal distribution. You may be tempted to think, if that's the case, then when my sample size is large, I'm better off switching to a parametric method because it also uses the normal distribution. Not so fast. While it is true that the large sample approximation of a nonparametric method when you are using original scores is in fact the parametric counterpart, for example, the large sample approximation for one sample inference using Fisher's method with original scores is the one sample t-test and associated confidence interval. However, the large sample approximations do not yield the same results as the parametric counterpart if you're using replacement scores. Furthermore, there are going to be power differences among the various methods, both parametric and nonparametric, depending on the nature of the population distribution, even when you're using large sample approximations. So to summarize the main point that I'm trying to make here, the fact that you're going to use a large sample approximation does not mean it's now time to use parametric methods. The large sample approximation for a nonparametric method with some population distributions will still yield more powerful results, just as when you're using an exact method. The only difference here is that we're now using an approximation instead of an exact method, but all the other principles regarding how to obtain the most power still hold. While I cannot go into all the possible large sample approximations for all the methods that we are going to visit in these video series, we can look at a couple examples, starting with the Wilcoxon signed ranks large sample approximation. The mean and standard deviation of t, the sum of the positive ranks, that is the test statistic we use when we use the Wilcoxon signed ranks method, is known when the null hypothesis is true. Here are the formulas for the mean and the standard deviation. Because the central limit theorem says that with a large enough sample, t will be distributed approximately as a normal distribution, I can use this mean and standard deviation to calculate a z-score for my particular test statistic, then use the normal distribution to come up with an approximate probability. The fact that we're subtracting the mean of our test statistic under the null hypothesis from the observed value of the test statistic, then dividing by the standard deviation of the test statistic, should be well known to you by now. It is the basis for much of the inference you do in a first statistics course. But what is this plus and minus half? That is known as the correction for continuity. Remember that your test statistic, t, is really not continuous. You're obtaining discrete values. That's always the case when we do research. But yet we're using a normal distribution, that is, a continuous mathematical model, to estimate our probabilities. This correction for continuity is taking halfway between the potential jumps of t. Remember that t is in ranks, and so the jumps are in increments of 1. It's taking half of that and using that halfway point as the correction for continuity. Furthermore, we make the choice to add or subtract so as to reduce the value of z, thus decreasing the probability of rejecting the null hypothesis, which gives us a better chance of maintaining our type 1 error rate when we use this approximation. Let's look at an example. In past videos, I used for the values of my observations 3, -2, 7, 6, -1, and 12. I'm going to use those again. Now note, this is not a large sample. There is no problem conducting exact methods and calculating exact probabilities with these values. But in order to exemplify the large sample approximation and keep it simple, I'm going to still go ahead and use these 6 values. Normally, we would not be doing a large sample approximation here. You may or may not recall when we did this example with the Wilcoxon signed ranks test that the sum of the positive ranks was 18. That is, we ranked all these values without regard to whether they were positive or negative, considering them all as positive, but then we only added up those ranks that were associated with positive original scores. That gave us 18. Using the formulas I just presented, with a sample size of 6, we can calculate the mean of t under the null hypothesis to be 10.5, the standard deviation of t to be 4.77, and then calculating our z statistic, we get 1.47. That is, we take our test statistic of 18, subtract the mean, then subtract another half. Remember, this is the correction for continuity, and we should subtract here because it will make z a little bit smaller, and then divide that all by 4.77, and it gives us a z of 1.47. Here I'm calculating z to a few more decimal points, so we get a little more accuracy when we calculate a probability, even though the calculation is going to result in an approximation. Using my statistical software, I find that the probability that z is greater than or equal to 1.4676 is 0.0711. So the p-value for a t of 18 using a large sample approximation is 0.0711. Now just for grins, even though we only have 6 values here so it's nowhere near a large sample, I'm curious as to what the exact value is. Here's the probability table. For our t of 18, notice that the probability of getting 18 or greater than 18 is 0.078. So we had an approximate value of 0.071 and an exact value of 0.078. Considering that we had only 6 observations, you should be quite impressed with this approximation. Let's do one more example. Let's use normal scores and calculate the large sample approximation. The mean and standard deviation of t, this time the sum of the positive normal scores, is known when conditioned on the null hypothesis. Here's the mean, here's the standard deviation. By the central limit theorem, t is distributed as a normal distribution, so we will calculate z by taking t and subtracting the mean of t and dividing by the standard deviation of t. There is no correction for continuity here because we're already drawing our normal scores from a normal distribution. Remember to keep all the normal scores positive when using these formulas. That is, even though you're only going to add up the positive normal scores when you calculate your test statistic, you need to add them all up when you calculate the mean and standard deviation. Using the same example of 3, -2, 7, 6, -1, and 12, here are my normal scores, and the t statistic, the sum of the positive normal scores, is 3.89. I use all of these normal scores without the negative signs in order to calculate the mean of t of 2.218, the standard deviation of t of 1.0488, and the z statistic is my observed t of 3.89 minus the mean divided by the standard deviation. I get 1.594. When I use my statistical software to calculate the probability of obtaining at least 1.594 with a normal distribution, it is 0.055. Again, for grins, let's take a look at the exact distribution table. Here it is. The probability of obtaining a test statistic greater than or equal to 3.89 is 0.0625. Again, not bad comparing 0.055 to 0.0625, considering that we only had 6 observations. Remember that the larger the number of observations, the better the approximations. That's serendipitous, because when are we going to need to use large sample approximations? When we have many observations.